welcome to True Projects. In this video, we are going to explain about the project entitled as Efficient Approach for Brain Tumor Detection and Classification using Fuzzy Thresholding and Deep Learning Algorithms. So before getting into the video, let me give you the brief description about the project. This project presents an efficient approach for automated brain tumor detection and classification using fuzzy thresholding and deep learning algorithms. Fuzzy logic is employed to accurately segment tumor regions from MRI images by handling intensity, uncertainty, and noise. By deep learning models then extract meaningful features and classify tumor types in high precision. The proposed system aims to improve diagnostic accuracy, reduce manual effort, and support clinical decision making. Coming to the abstract explains the importance of accurate brain tumor detection and classification in medical diagnosis, and it directly influences patient treatment and outcomes. It highlights the limitations of traditional manual analysis of MRI or CT scans, which can be slow and error prone. To address these challenges, the project introduces a hybrid approach that combines fuzzy thresholding for precise tumor segmentation with deep learning models for automated and accurate classification. By improving boundary detection and reducing human dependency, the proposed system enhances diagnostic speed, accuracy, and reliability, ultimately supporting better clinical decision making. Coming to the existing system for brain tumor detection largely relies on traditional image processing techniques combined with manual analysis by medical experts. Common methods such as edge detection, region growing, and simple thresholdings are used for segmenting tumor regions, but they often perform poorly when dealing with noisy MRI images, low constraints, and complex tumor shapes. For classification, convolutional machine learning algorithms like SVM and KNN are employed, which depend heavily on handcrafted feature extraction and extensive pre processing. As a result, this system tends to be time consuming, less accurate, and highly dependent on expert involvement, limiting their efficiency and scalability. Coming to the proposed system or base paper work, the proposed system improves brain tumor detection and classification by integrating fuzzy thresholding with advanced deep learning techniques. Fuzzy thresholding is used to accurately segment tumor regions from MRI images by effectively handling noise, intensity variations, and unclear boundaries. After segmentation, convolutional neural network automatically learn and extract relevant features to classify tumors into different categories such as benign or malignant. This automated approach reduces the need for manual feature extraction, enhances accuracy, speeds up diagnosis, and offers a reliable and efficient solution for supporting medical decision making. Coming to the dataset, we have used three different datasets. Let us check one by one. First, the brain tumor classification MRI dataset. The brain tumor classification MRI dataset is a publicly available collection of brain MRI images designed for tumor classification research. The dataset is categorized into four distinct classes: glioma, benign glioma, pituitary tumor, or no tumor. It is primarily used to train and evaluate machine learning and deep learning models for multi-class classification tasks. The dataset is typically divided into training and testing sets, enabling effective model validation and performance analysis based on labeled MRI images. Second, we used brain tumor MRI dataset. The brain tumor MRI dataset available on Kaggle is a large-scale dataset created by combining multiple public MRI sources. It contains thousands of brain MRI images classified into four categories. Due to its large size and diversity, this dataset is well suited for deep learning applications, particularly convolutional neural networks. The images are generally provided in grayscale JPG format and can be pre-processed through resizing, normalization, and data augmentation to enhance model performance and generalization. Third, we used brain tumor MRI classification data set. The brain tumor MRI classification dataset selected as an alternative to a dot mat based dataset consists of organized MRI brain scans labeled for tumor classification task. Depending on its structure, the dataset supports both binary and multi-class classification. Each MRI image is annotated accordingly to tumor presence or tumor type, making it suitable for supervised deep learning approaches. This dataset is commonly used as a benchmark for evaluating automated brain tumor detection and classification models, with images typically arranged in labeled folder or accompanied by annotation files. Coming to the novelty or extension or enhancement or improvement. As an extension, advanced deep learning models such as exception are implemented to improve classification performance. In addition, a hybrid model combining two deep learning architectures is used to leverage the strength of multiple models, resulting in better accuracy and robustness. The YOLO family of models is applied for detecting abnormalities in MRI images. These models not only classify the tumor type but also localize the tumor region by generating bounding boxes, enabling real time and precise tumor detection. Furthermore, explainable AI techniques such as GradCam are employed to generate heat maps that highlights important regions of MRI image influencing the model's prediction. This improves transparency and helps in understanding the decision-making process of deep learning models. Along with that, a Flask based is used to develop a user friendly web interface where users can upload MRI images and obtain predictions from the trained models. The interface displays detection results, predicted tumor classes, and confidence scores, making the system accessible and practical for real world use. Coming to the flow of the work, first let us check with the segmentation workflow. First, we have pre processing. MRI images are converted to grayscale and an adaptive fuzzy threshold is computed using histogram based fuzzy membership functions to handle intensity variations effectively. In pre-processing, we have fuzzy segmentation mask generation. Pixels above the fuzzy threshold are extracted to form a tumor mask which is smoothed using Gaussian filtering and converted into a binary segmentation mask. In pre-processing, next we have tumor size calculation. The number of tumor pixels in the binary mask is counted and expressed as a percentage to the total image pixel to estimate tumor size. Next, preparing data for segmentation training. Images are resized to 256 into 256, normalized, transposed to channel first format, and paired with generated mask for model training. Next, dataset and data loaders. Segmented images are split into training and validation sets and loaded into data loaders with a batch size of 8. Next, build and train the model. A CNN-based segment model is trained using the prepared data, and the trained weights, configuration, and state dictionary are saved. Coming to the classification workflow, first we have pre-processing fuzzy threshold. Fuzzy thresholding and segmentation are applied again to highlight tumor regions before feature extraction and classification. Next, we have image data augmentation. Segmented images undergo augmentation such as rotation, resizing, and tensor conversion to improve model generalization. Next, dataset integration and YOLO setup. All three datasets are merged into an unfined dataset and a YOLO data configuration file is created for tumor detection task. Next, we have maintain parallel datasets. Two parallel inputs are maintained. Image label pairs for classification model and image bounding boxes pairs for YOLO detection model. And for classification model training, multiple baselines, proposed, and extension deep learning models are trained to classify tumor types with hyperparameter tuning and ensemble learning used for performance improvement. And for YOLO based tumor detection training, YOLO V5, YOLO V8, YOLO V9, and YOLO V11 models are trained to simultaneously localize tumors and predict their classes. Next, model evaluation and comparison. Classification models are evaluated using accuracy, precision, recall, FN score, and confusion metrics, while YOLO models are assessed using MAP, precision, and recall. And next, we have interface and deployment using Flask. A Flask-based web application takes an MRI image as input, performs detection and classification, and displays the bounding boxes predicted tumor class and confidence score. The algorithms used in the project are baseline models, MobileNet V2, EfficientNet B0, B4, and B7, ResNet 50 and 101, VGG 16 and 19, Inception V3, DesNet 121, DenseNet 121 and 201, and WIT. Proposed model is used CNN hyperparameter tuning, and as an extension model we used exception ensemble, which consists of exception plus DesNet 121 for dataset 1 and 2, exception plus DenseNet 201 for dataset 3. And extension for YOLO based detection model, we have used YOLO V5, YOLO V8, YOLO V9, and YOLO V11. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consisting of operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consist of application framework Anaconda, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3. Technologies which we use to build the front-end are HTML, CSS, JavaScript, and Bootstrap 4. To execute the project first, we need to open the code folder which contains project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test, and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. Models file. These are the model files which contain the algorithm information which will be loaded into the project code during the runtime. IPYNB files. These are the Jupyter Notebook files which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This is a database file used to store the user information. Now, coming to the execution of the project, firstly, you need to copy the path of the code folder from the address bar of the file explorer. Then open Anaconda prompt. Use the command cd followed by a space and paste the copied path. This command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py in the Anaconda prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the local link provided by the framework and paste it in any web browser. I prefer Chrome. The home page of the project should now be displayed in the browser. This is a front-end built using Flask framework. In this page, we have home button, user login button, and get register button. Firstly, click on get register button so that the create account form will be opened where you need to enter the details and create an account for user authentication by entering the username, full name, mail ID, contact number, and a strong password. Then click on sign in so that all the given details are stored in signup.db and login.html will be opened where you need to enter the username and password to access the application. Then click on sign in. The prediction page has been displayed. In this page, we have prediction button, graphs button, notebook button, and logout button. Firstly, click on prediction button so that the classification and detection will be open. Let us check one by one. Firstly, We'll go with classification. Click on classification button so that upload MRI scan for analysis will be open, where you need to upload an MRI scan image and then classify the image. The image has been successfully uploaded, and then click on Analyze MRI scan so that the given image is pre-processed and the output will be displayed as glioma. The confidence level is 100%. Here we have the tumor coverage, total pixels and processing time. We also have the segmentation results like the original MRI scan image and fuzzy threshold mask image. And we also have deep learning mask image and masked image. Finally, we have the heat map visualization image, and confidence scores are also given like it is a glioma, that 100% has been satisfied. And we also have important information like glioma is detected, and let us click on analyze other image so that the form will be opened again. Let us browse an image. The image has been successfully uploaded. Click on analyze MRI scan so that the given image is pre-processed and the output will be displayed as benign glioma. The confidence level is of 100%. We have the tumor coverage, total pixels and processing time. We also have the image analysis like the segmentation results, the original MRI scan image, fuzzy threshold mask image, deep learning mask image, masked image, and also heat visualization image. And here we have the classification probabilities like the confidence score. Benign glioma, it is 100%. And we also have the information like medical recommendations of benign glioma detected. Then click on analyze other image. The form will be opened again where you need to upload the image. The image has been successfully uploaded. Click on Analyze MRI scan so that the given image is pre-processed and the output will be displayed as no tumor. The confidence level is of 100%. We have the total coverage, total pixels, processing time, and we also have the image analysis like segmentation results of original MRI scan, fuzzy thresholding mask, deep learning mask, masked image, and also heat map visualization. Here we have the classification probabilities like the confidence score for new tumor is of 100%. And we also have the important information like medical recommendations. No tumor has been detected. Then click on Analyze Other Image. The form will open where you need to upload the image. The image has been successfully loaded, and click on Analyze MRI scan so that the given image is pre-processed and the output will be displayed as pituitary. And the confidence level is of 100%. Here we have the tumor coverage, total pixels, processing time. And we also have the image analysis like segmentation results, original MRI scan image, fuzzy thresholding mask image, deep learning mask image, masked image, and also heat map visualization image. And we also have the classification probabilities like confidence score for pituitary, it's given as 100. And we also have the important information like medical recommendations for pituitary tumor detected. As we have seen for classification, now let us check for detection. Click on prediction button. Detection will be displayed, and click on detection button so that the brain tumor detection system upload your MRI image form will be open. You need to upload the image of MRI scan. The image has been successfully uploaded, and click on detect tumor so that the given image is pre-processed and the output for the image will be displayed as glioma has been detected in this part of the image. Okay, we also have about this detection given below, and click on analyze other image so that you can upload an image. The image has been successfully uploaded. Click on detect tumor. The given image is pre-processed and the output is displayed as benign glioma. And about the detection, it's given clear. And then click on analyze another image so that the form will be opened again where you need to upload the image of other. The image has been successfully uploaded, and click on detect tumor. The given input image is pre-processed and the output is displayed as pituitary in an bounding boxes. So about the detection is given clear. and then click on Analyze Other Image, so that the uploadation form will be opened again, where you need to browse the image, upload the image, and click on Detect Tumor, so that the given image is pre-processed and the output will be displayed as no tumor has been detected in a bounding boxes. About the detection is given clear here. And now let us check with graphical representations. Click on Graphs button. As we are dealing with classification and detection, let us check one by one. Firstly, click on Classification, so that the classification graphs will be displayed. As we are using three different data sets, let us check graphs for each different data set. Firstly, for data set 1. First, we have confusion matrix graph. This confusion matrix shows that the ensemble model classifies all four classes with high accuracy, as most values lies on the diagonal. Only a few misclassifications occur between tumor type, indicating strong overall performance and good class separation. Next, we have accuracy by model graph. The bar chart compares classification accuracy across different models, showing that ensemble exception DenseNet 121 and Inception V3 achieves the highest performance. EfficientNet V7 and VIT shows comparatively low accuracy, highlighting variability in model effectiveness for this task. Next, we have precision by model graph. This bar chart compares precision across models, showing that Ensemble, Exception, DenseNet 121, and Inception V3 delivers the most reliable positive predictions. Lower precision in EfficientNet B7 and the proposed CNN indicates a high rate of false positives. Next, we have recall by model graph. The recall comparison shows the ensemble exception DenseNet 121 and Inception V3 achieves the highest recall, meaning they detect most true cases correctly. Lower recall is in EfficientNet B7. The proposed CNN and VIT indicates a higher chance of missing positive samples. Next, we have F1 score graph. The graph shows the F1 scores across model, indicating overall balance between precision and recall. Ensemble, Exception, DenseNet 121 and Inception V3 achieves the highest F1 scores, while EfficientNet B7 and VIT performs comparatively low. And next we have dice by model graph. The dice score comparison shows that Ensemble, Exception, DenseNet 121 and Inception V3 achieves the highest overlap between predicted and true regions. EfficientNet B7 and proposed CNN has noticeably lower dice score, indicating weaker segmentation performance. Next, we have specificity graph. This graph compares specificity across models, showing that Ensemble, Exception, DenseNet 121, and Inception V3 achieve near perfect ability to correctly identify negative cases. EfficientNet B7 and VIT have relatively lower specificity, indicating a higher rate of false positives. Next, we have sensitivity graph. This graph compares the sensitivity across models, showing that Ensemble, Exception, DenseNet 121, and Inception V3 achieve nearly perfect ability, and EfficientNet B7 and VIT have relatively lower sensitivity, indicating a high rate of positive values. Next, let us check the graphs for dataset 2. In this, first we have confusion matrix graph. This confusion matrix shows that the ensemble model achieves very high classification accuracy, with most predictions concentrated along the diagonal for all four classes. Only a smaller number of misclassification occurs between tumor types, indicating strong and reliable model performance. Next, we have accuracy by model graph. The graph compares accuracy across different models, showing that the ensemble, Exception, DenseNet 121 and Inception V3 achieves the highest accuracy. EfficientNet B7 and proposed CNN performs comparatively low, highlighting differences in model effectiveness. And next we have precision by model graph. The precision comparison shows that Ensemble, Exception, DenseNet 121 and Inception V3 achieves the highest precision, indicating very accurate positive predictions. EfficientNet B7 and the proposed CNN shows relatively low precision, suggesting more false positive classifications. Next, we have recall by model graph. This graph compares recall across models, showing that ensemble exception density 121 and inception V3 achieves the highest ability to correctly identify true positive cases. EfficientNet B7 and the proposed CNN have comparatively low recall, indicating a higher chances of missed detections. Next, we have F1 score graph. The bar chart compares F1 scores across different machine learning models, showing how well each balances precision and recall. Most deep methods achieve very high performance near 1.0%, while efficient at B7 and the proposed CNN perform relatively low, indicating weaker overall classification performance. And next we have dice by model graph. The bar chart shows the dice coefficient for different models, indicating how well predicted output overlaps with the grounded truth. Most models achieve high dice scores close to 1.0%, reflecting strong segmentation performance, while efficient at B7 and the proposed CNN shows noticeably lower overlap compared to the top performing models. Next, we have specificity by model graph. The bar chart compares specificity across different models, reflecting their ability to correctly identify negative cases. Most models achieve very high specificity near 1.0%, indicating low false positive rates, while efficient at B7 shows slightly lower performance compared to the others. Next, sensitivity by model graph. The bar chart compares the sensitivity of different machine learning models. Most models shows very high sensitivity, indicating strong ability to correctly detect positive with exception ensemble densenet variance and inception V3 performing best, while efficient at B7 shows comparatively lower sensitivity. Now, let us check with data set 3 graphs. In this, first we have confusion matrix graph. The confusion matrix shows that the ensemble model classifies all four brain tumor classes with very high accuracy, as most value lies on the diagonal. Only a few misclassification occurs between similar classes, indicating strong overall performance and minimal confusion. Next, we have accuracy by model graph. The bar chart compares the classification accuracy of different machine learning models. Most deep learning methods achieve very high accuracy, with ensemble and exception performing the best, while efficient at B7 shows noticeably lower accuracy compared to others. Next, we have precision by model graph. The bar chart compares the precision of different ML models. Most models achieve very high precision, with ensemble exception density 201 and inception V3 performing best, while efficient at B7 shows noticeably lower precision than the others. Next, we have recall by model graph. The bar chart shows the recall performance of different ML models. Most models achieve very high recall, indicating strong ability to detect positive cases, while efficient at B7 and the proposed CNN have comparatively low recall than the top performing models like Ensemble, Exception, and DenseNet 201. Next, we have F1 score by model graph. The graph compares the F1 scores of different ML models, reflecting the balance between precision and recall. Most models achieve very high F1 scores, with ensemble, exception, and densenet performing the best, while efficient at B7 and the proposed CNN shows relatively lower overall performance. Next, we have dice by model graph. The bar chart compares dice scores across different machine learning models, showing how well each model performs. Most models achieve high dice values, indicating strong performance, while EfficientNet B7 and the proposed CNN stand out with noticeably lower scores. Next, we have specificity by model graph. The bar chart shows the specificity of different machine learning models, indicating how accurately each model identifies negative cases. Most models achieve very high specificity, with EfficientNet B7 slightly lower, with VID, ensemble, and exception demonstrate near perfect performance. Next, we have sensitivity by model graph. The bar chart compares the sensitivity of different machine learning models, reflecting their ability to correctly detect positive cases. Most models shows high sensitivity with efficient net B7 and the proposed CNN perform relatively low, indicating more missed positives. As we are clear with classification graphs, now let us check with the detection graphs. In this detection graphs, first we have YOLO precision graph. The bar chart compares the precision of different YOLO models. YOLO V5 shows the highest precision, followed closely by YOLO V8 and YOLO V9, while YOLO V11 has the lowest precision among the four. Next, we have YOLO recall graph. The bar chart shows the recall performance of different YOLO models. YOLO V8 achieves the highest recall, meaning it detects the most true objects, while YOLO V11 has the lowest recall, with YOLO V5 and YOLO V9 performing in between. And next we have YOLO MAP score graph. The bar chart compares the mean average precision of different YOLO models. YOLO V8 achieves the highest overall detection performance, followed by YOLO V5 and YOLO V9, while YOLO V11 shows the lowest MAP among the models. And next, click on Logout. So finally, this project presents an efficient and reliable approach for brain tumor detection and classification by integrating fuzzy threshold with deep learning algorithms. The use of fuzzy logic improves accurate tumor segmentation, while deep learning models enable automated and precise classification of tumor types. The proposed system reduces manual effort, enhances diagnostic accuracy, and supports faster clinical decision making. Overall, the approach demonstrates strong potential for real world medical imaging applications. This is all about your project. Thank you.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.